The Gaia Space Telescope is a remarkable tool launched by the European Space Agency, ESA, with a mission to create the most detailed 3D map of our galaxy, the Milky Way. It carefully tracks billions of stars, measuring their positions, distances, and movements with astonishing precision. This level of detail allows astronomers to unravel the complex tapestry of our galaxy's past and present. Recently, Gaia achieved an extraordinary feat by identifying 55 runaway stars speeding away from a tightly packed young star cluster known as R136, located in the Large Magellanic Cloud. This is a rare sight. Never before have so many runaway stars been spotted escaping a single cluster. The Large Magellanic Cloud, a satellite galaxy of our Milky Way, is home to R136, a dense cluster packed with some of the most massive stars we know. These stars, some with 300 times the mass of the Sun, were born in a massive stellar nursery just 1.8 million years ago, a blink of an eye compared to our 4.6 billion-year-old solar system. The discovery of runaway stars offers us a glimpse into the cluster's dynamic environment. It reveals that R136 has already experienced two significant episodes where stars were flung out at speeds of over 62,000 miles per hour. The fact that this phenomenon is happening in such a young cluster shows just how dramatic and energetic these environments can be. It's thrilling for scientists to uncover such mysteries. With Gaia's ability to monitor the precise movements of stars, we've expanded our understanding of stellar behavior. This discovery alone increased the known population of runaway stars by a factor of 10, marking a groundbreaking moment for astronomical research and showing just how much Gaia is pushing the boundaries of what we know about our universe. R136 isn't just any star cluster, it's a bustling, young, and vibrant nursery of stars located around 158,000 light-years away in the Large Magellanic Cloud. This stellar cluster is packed with hundreds of thousands of stars, many of which are among the largest and most massive ever discovered. Stars here can be up to 300 times the mass of our Sun, illuminating the region with intense light and heat. This environment is a powerhouse of star formation, making it an ideal place for astronomers to study the life cycles of massive stars and observe the raw forces that shape them. Among this cosmic chaos, astronomers have identified 55 runaway stars, stars that have been ejected from the cluster at mind-boggling speeds. These stars are racing away from their birthplace at over 62,000 miles per hour, about 80 times faster than the speed of sound on Earth. The incredible energy required to propel them to such speeds tells us that powerful gravitational interactions are at play in the cluster. The runaway stars were expelled from R136 in two distinct bursts. The first of these events took place around 1.8 million years ago, shortly after the cluster's formation, as the gravitational dynamics of tightly packed young stars forced some to break free. Then, more recently, about 200,000 years ago, a second ejection episode occurred. But unlike the first, this second episode saw stars being launched in a preferred direction and at somewhat slower speeds. This deviation hints that different mechanisms were likely at work, adding another layer of mystery to the findings. Interestingly, these runaway stars are not just moving at high velocities, they're also potential cosmic time bombs. Many of them are massive enough to end their lives as supernovas, which could create black holes or neutron stars that will travel even further from the cluster. Over the course of millions of years, these remnants may explode as far as 1,000 light-years from their origin, spreading heavy elements throughout the galaxy. By observing the intricate dynamics within R136, astronomers are piecing together how such clusters evolve and the role they play in the broader cosmic landscape. This is no simple environment, it's a place where stars are born, live intense lives, and sometimes meet dramatic ends as they are flung across the universe. The story of R136's runaway stars is a fascinating case of cosmic dynamics and gravitational dance. Over the past 2 million years, the cluster has experienced two significant episodes of ejection, each with its own characteristics and implications. The first episode, which occurred roughly 1.8 million years ago, was marked by the chaotic ejection of stars in random directions, a testament to the high-energy environment of the young cluster. As massive stars formed close to one another, their intense gravitational pulls created instability, flinging some stars out into the vastness of space. This process highlights how the birth of stars in such close quarters can lead to dramatic encounters, with gravity acting as a powerful, invisible hand that shapes their destinies. The second episode, more recent at about 200,000 years ago, was intriguingly different. Rather than random ejections, this burst saw stars moving away in a preferred direction and at somewhat slower speeds. This suggests that some specific gravitational event or change in the cluster's structure could have caused this directed escape. It's possible that interactions with another star or a collective movement within the cluster disrupted the orbits of these stars, giving them the final push they needed to break free. These differences in ejection patterns offer astronomers crucial clues into the internal mechanics of our 136, helping them understand the diversity of events that can occur even within a single star cluster. Such runaway stars aren't just notable for their speeds, they're essential for unraveling the mysteries of cluster dynamics. By studying the directions and velocities of these stars, astronomers can backtrack their movements and gain insights into the history and evolution of our 136. This research helps us understand how stars and clusters like our 136 can interact so intensely that they alter one another's paths, leading to a chain reaction of ejections and, ultimately, the cluster's gradual dispersal. These high-speed stars also carry a significant cosmic payload. Many of them are massive enough to end their lives in supernova explosions. When this happens, they will not only release vast amounts of energy but also distribute heavy elements like carbon, oxygen, and iron into the surrounding space. This process enriches the interstellar medium, seeding future generations of stars and planets with the building blocks of life. In this sense, runaway stars contribute to the grand recycling system of the universe, spreading the elements that will eventually become part of new stars, solar systems, and even life itself. The runaway stars from our 136 are therefore more than just high-speed travelers, they are cosmic messengers, carrying clues about their violent origins and impacting the future of the universe with each explosive end. This complex interplay of gravitational forces and stellar evolution reveals the intricate and interconnected nature of our cosmos, showing us how even the most isolated stars are part of a larger cosmic story. The ejection of runaway stars from our 136 isn't merely a spectacle, it provides a window into some of the most profound processes that govern star formation and galactic evolution. When stars are born in clusters, especially ones as densely packed as our 136, the interactions between them can be both unpredictable and incredibly violent. As these massive, young stars form in close quarters, they engage in gravitational battles that often end with some stars being catapulted out of the cluster. This phenomenon is more than a random occurrence, it's a key part of understanding how star clusters evolve over time and how galaxies, in turn, grow and change. In clusters like our 136, massive stars tend to form in chaotic environments where close encounters with other stars are almost inevitable. These encounters can result in one or more stars being gravitationally slingshot out of the cluster at incredibly high speeds. The process is called dynamical ejection, and it highlights the immense gravitational forces at play. A close pass between two or more massive stars can alter their orbits so drastically that one star gains enough momentum to escape the gravitational grip of the cluster entirely. This is what happened in our 136, where 55 stars were thrown into the void in two separate episodes, each marked by distinct gravitational circumstances. The timing and nature of these two ejection events also reveal different stages of cluster evolution. The first episode occurred during the cluster's formation, likely influenced by the initial surge of star births and the intense gravitational pull within the young, dense cluster. This event sent stars in various directions, almost like the initial jolt of fireworks. The second episode, however, was more directional, suggesting a shift in the internal dynamics of our 136. Perhaps a particularly massive star or a tightly bound group of stars interacted in a way that produced a more controlled, directional ejection. Understanding this sequence of events gives astronomers valuable insight into how clusters mature and how their internal structures influence the fate of individual stars. Astronomers believe that gravitational interactions are not the only factor at play in runaway star ejections. Supernova explosions within the cluster might also contribute to the process. In a crowded stellar nursery like R136, the death of a massive star as a supernova could generate enough energy to disrupt the orbits of nearby stars. The shockwave from such an explosion could push stars outward, aiding in their escape from the cluster. This adds another layer of complexity to the dynamics, as the cluster's most massive stars essentially pave the way for the ejection of their stellar companions. The runaway stars from R136 may be witnesses to these explosive events, carrying with them the signature of the cluster's violent internal processes. Moreover, runaway stars play a crucial role in the broader galactic ecosystem. As these stars travel through space, they act as cosmic pollinators, dispersing heavy elements essential for the formation of new stars and planets. When they end their lives in supernova explosions, they release these elements into the interstellar medium, enriching it with the raw materials needed to form complex molecules and, eventually, life itself. This process, known as stellar nucleosynthesis, is a cornerstone of cosmic evolution. It's a reminder that even the most dramatic events in the cosmos, such as the ejection of runaway stars, contribute to the ongoing cycle of birth, death, and rebirth that sustains the galaxy. The study of runaway stars like those from R136 also challenges our understanding of star cluster dynamics. Observing these ejections helps astronomers refine models of cluster evolution, shedding light on how star clusters dissolve over time and how they contribute to the galactic population of stars. The discovery that R136 has experienced multiple episodes of ejection indicates that star clusters might be less stable than previously thought, with stars regularly being cast out into the galactic wilderness. This newfound understanding of cluster behavior could reshape our view of how galaxies populate themselves with stars and how the Milky Way itself has come to harbor its diverse stellar population. Finally, the fact that these runaway stars were identified in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, highlights the intergalactic scale of these processes. It demonstrates that the forces shaping our own galaxy are not isolated but are part of a much larger cosmic web of interactions and events. Gaia's observations of R136 not only expand our knowledge of runaway stars but also offer a glimpse into the broader tapestry of our universe, where galaxies and star clusters interact and evolve in a grand, interconnected dance. By tracking these stars as they journey through space, astronomers are piecing together a story that stretches across the cosmos, illuminating the forces that govern the life and movement of stars throughout the universe. The discovery of R136 runaway stars redefines our understanding of star clusters and galactic dynamics. By tracking these stars, Gaia unveils the powerful gravitational interactions that can shape, disrupt, and even disperse entire clusters. Each runaway star becomes a cosmic ambassador, carrying with it the story of violent origins and contributing to the galactic cycle by seeding the universe with essential elements. This cosmic narrative isn't just about distant stars, it's a reminder that our galaxy is alive, constantly evolving, and intricately connected. If you're fascinated by the mysteries of space and want to support more explorations like this, consider joining us in our journey. Subscribe, share your thoughts in the comments, and help fuel further research by contributing to our channel. Together, we can keep unraveling the universe, one star at a time.